In this video, we're going to introduce ourselves to a new way of visualizing atoms, and as you can imagine from the title here, that's going to be Lewis diagrams. But before I even get into that, let's do a little bit of review of what we already know about Bohr models. So let's say we take an arbitrary element here. Let's say we take nitrogen. Nitrogen, by definition, has 7 protons, and so if it's neutral, it's going to have 7 electrons. So a Bohr model for nitrogen, in our first shell, that first shell is going to look just like helium, and it's going to have 2 electrons. So let me draw it like that. And then in its second shell, it is going to have the remaining 5 of the 7 electrons. And we are going to make them unpaired at first. So 1, 2, 3, 4, and then 5. The reason why I did it this way is a full valence shell is going to have 8 electrons, or 4 pairs. But if the electrons can spread apart, they like to spread apart. So that's why I did 1, 2, 3, 4, and then I paired this last one because there's nowhere else for it to actually go. Now, I just touched on this issue of valence electrons. Those are the electrons in your outermost shell, and they tend to be the ones that are involved in reactions. So chemists said, hey, just for a shorthand, instead of having to draw all of this every time, why don't we just visualize the valence electrons? And so let's do that in this nitrogen example. So a Lewis diagram, which is I'm just going to draw right now, is that simplified visualization where you write the symbol for that element and you just depict its valence electrons. We just saw that there are 5 valence electrons for nitrogen, 7 total, but 5 valence, 5 electrons in that outermost shell. So it is going to be 1, 2, 3, 4, and then 5. So that's a Lewis diagram for a neutral nitrogen atom. It turns out we can also do this for ions. So let's say that we had a nitride ion over here. Now, a nitride ion has gained 3 electrons. So it actually has 8 valence electrons. So if you gain 3 from 5, you're going to have 8. So I'll go 1, 2, 3, 4, 5, 6, 7, 8. And because it gained 3 electrons from being neutral, it now has a -3 charge. And so you'll often see it written like this, where they put brackets around it, and you would see 3 minus. Now, the last thing that you might wonder about is, okay, I kind of understood how you got the valence electrons for nitrogen. Is there just some general pattern in the periodic table? And the simple answer is yes. And that's one of the useful things about the periodic table. Or as we'll learn, there's many, many other really interesting things about it. If you look at the groups, in general, you're going to have 1 valence electron for group 1 elements for this column over here. You're going to have 2 valence electrons for these group 2 elements. And I know what you're thinking. Okay, is just the group the number of valence electrons? Well, unfortunately, it doesn't exactly work out that way. I'm going to skip the transition metals here because those get a little bit more complicated. It's a little bit more advanced. But then if we go over here to, what is this, group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Group 13 over here is going to have 3 valence electrons. Group 14, 4 valence electrons. 5 valence electrons in group 15, and that's why we saw 5 valence electrons for nitrogen here. 6 for group 16, 7 for group 17, and then 18 for, or sorry, I should say 8 valence electrons for group 18. So one way to remember it is, for groups 13 through 18, you take the group number and you subtract 10, and you're going to get the number of valence electrons. And hopefully that made sense based on how we were able to figure out the valence electrons for example, nitrogen.